In this video, we'll be looking at nucleophilic substitution reaction, and we would be looking at SN1 mechanism. SN1 mechanism. Now, SN1 basically stands for unimolecular nucleophilic substitution. Unimolecular substitution reaction. Alright, now this reaction gives you the same result as SN2 mechanism, but then that means it's also accompanied by the substitution of the leaving group on a substrate. Now, what is important to take note of here is that only one species is involved in the rate determining step. And so we have the rate equation, which is given as R equals K, and then we have square brackets RL. Alright, so that means the K here is a rate constant. The R is a substrate, and the L is the leaving group. Okay, so I want you to notice that in this rate equation, we are not including the nucleophile. So it is a reason why it is referred to as unimolecular substitution reaction. That means the rate of the reaction actually depends on the concentration of the substrate. Alright, now what does the mechanism looks like? For the mechanism, if we have a carbon bonded to, let's say, 3 different groups, X, Z, and Y, and then we have a leaving group L attached. Now what is going to happen is that the L is more electronegative, making it to become partially negative, while the carbon becomes partially positive. So the first step of this reaction involves the breaking away of the leaving group. So we have the leaving group going out, which is a very slow process, and it's going to give us the intermediate. The intermediate is a carbocation. So we are going to have the Y, and we are also having the Z attached, but this time carbon has a positive charge. So the leaving group goes out as a nucleophile this time. So basically what we have here, this is a planar carbocation. What we have there, the carbon is sp2 hybridized. So these bonds, we have 6 bonding electrons here, but then we also have an empty p orbital over there, which is where the leaving group will be attacking on the carbon to form the last bond. Okay, now once we have the carbocation being formed, what happens next is that we are going to have, so I'm going to clean this. We are going to have the nucleophile coming in to attack the carbocation. So again, we have the carbocation C bonded to X, and then we have Y, and the positive charge here. Now we are going to have the nucleophile coming in from one side and attacking the carbocation, which is a very fast reaction. and we are going to have the products, the nucleophile attached to the carbon. But this time, the geometry or the shape is going to change. We are going to have the X towards this direction. We are going to have the Z. We are also going to have the Y here. All right. Now, this can also occur from the other side when we have the nucleophile attacking from the other side. So we have X. Remember, this is Y, and this is Z. So we have Y here and Z. This time, when the nucleophile attacks from this direction, that means that the product we are going to have is going to be C bonded to the nucleophile at this side, and then the X is going to be here. We are going to have the Z and then the Y. So this is what we should be expecting. Now the first step involves what the loss of the leaving group, as we can see here, which is going to result in the formation of the carbocation. And then we have the nucleophile coming in, attacking from a particular side. If it's attacking from the left side, then the product is going to have this configuration. If it is attacking from this side, then the configuration is going to be the other way around. So what is happening here is that we are going to have a mixture, that is a racemic mixture, because it could either be the S conformer or the R conformer. So we have a mixture of two stereoisomers. All right. Now, we also have to take note that the slowest of this reaction is the formation of the carbocation, and so this carbocation step is actually the rate determining step, the RDS, because it is the slowest. The other part occurs really fast. It occurs really fast. Now, one other thing is that you notice that we have the carbocation, and so we don't really look at the nucleophilicity of the nucleophile which is coming into attack, because once the carbocation is formed, it becomes very reactive, which means that the rate of the reaction depends on the carbocation that is being formed. So automatically we are going to have the nucleophile coming in to attack the carbocation and form the product. So that is one of the factors that will affect the rate of the reaction. For this reason, we don't include the nucleophile in the rate equation. So we only have K and the concentration of the substrate. All right. Now, the third thing to take note of is that the formation of the carbocation is a reversible reaction. So what that means is that if the carbocation here is in excess more than the nucleophile, then that means that the nucleophile is going to get consumed, and then we are still going to have some carbocation in there. That means it can react with the leaving group which has been kicked off, or which has gone out, and form the initial compound back. So this rate determining step is also a reversible process. All right. Now I want us to take a look at what the energy profile diagram is going to look like. So if this is the graph, and I have the y-axis and the x-axis, over here we have energy. So this is energy, and this is the reaction pathway. Now, the graph is going to look like this. Now we have the reactants. So what is happening here is that if this is the energy of the reactants, they need to attain a certain activation energy to the transition state. So they need that activation energy to the transition state in order to be able to form the carbocation. So the carbocation, that is the first part of the reaction. And the second part of the reaction is the carbocation reacting with the nucleophile to give us the product. So this is the second transition state. So we have the second transition state, and then finally we have the product, which is going to be of a lower energy compared to the reactants. So basically, this is the reaction pathway in SN1 mechanism, which is quite different from what we have in the SN2 mechanism. Now, I want us to look at the reaction between butanol. So I have butanol and hydrogen bromide, HBr. Okay, so butanol we have CH3, CH3, and then the OH. So this is a tertiary alcohol. Now in this reaction, we want to replace the hydroxyl group of the alcohol with a bromide. So in order to perform this reaction, the first thing we need to do is to convert the hydroxyl into a good leaving group. And how are we going to do that? We do that by protonating the OH. So if this is the HBr, this bond is going to break heterolytic, and then we are going to have the electrons thrown to bromine. So the oxygen is going to pick the H and gets protonated. So we are going to have CH3, and then we have O with two hydrogens, which is making it to have a positive charge. Now H2O is a good leaving group compared to OH. So what is going to happen is this is going to break off, the CO bond is going to break, and we are going to have our reaction intermediate, which is a carbocation. So this is the rate determining step, and so it is very slow, RDS. Now we have the intermediates, CH3, and the carbon having a positive charge. So over there we have a tertiary carbocation. Remember, we are giving off water. Now, in the final step of the reaction, we are going to have the carbon, the tertiary carbocation, with a positive charge. And now the bromide reach an electron attacking the carbon, and it's a very fast process, giving us the butyl bromide. So again, CH3, and then Br. So this is the butyl bromide. Alright, so this is the mechanism in SN1 that takes place in SN1. Now, I want you to consider this. We have a tertiary carbocation, CH3, and then we also have a secondary carbocation, and a primary carbocation. So we have H here and H here. Now, which of these three is going to give you an SN1 mechanism. Alright, so for SN1 mechanism to take place, we need a really stable carbocation. Now, among these three, in terms of stability, the tertiary carbocation, so we have tertiary carbocation here, and we have a secondary carbocation and a primary carbocation. The tertiary carbocation is more stable than the secondary, which is also stable than the primary carbocation. So when we are talking about the rate of reaction with respect to SN1, we have the tertiary carbocation, which is going to have a rate of 1.2 times 10 exponent 6, which means it is very fast, compared to the secondary carbocation, which is going to give you 12, and the primary a rate of 1. Now, the reason for this is because the tertiary carbocation is really stable. Now, when we talk about the stability of carbocation, if we have an alkyl group, which is an electron donating group, it stabilizes the carbocation by dispersing the positive charge. Now, alkyl groups are very good in doing this, and the tertiary carbocation has 3 of such groups, a metal here, a metal here, a metal here, compared to the secondary carbocation, which has 2, and the primary carbocation, which has 1. So carbocations are stabilized by electron donating effects of alkyl groups. So this actually what helps it to become stable for an SN1 mechanism to take place. Now the reverse is true for SN2 mechanism. I hope you find this video helpful, and don't forget to subscribe and also share the links to your friends.